So we're going to finish looking at 7.5. So we've already done the sum and difference identities for sine, for cosine. The last group we have is for tangent. So technically, we don't need a separate formula for tangent because if you wanted to rewrite tangent as a fraction of two other trig functions, how could you do it? Yeah?
Sine over cosine.
Exactly. You could write it as sine over cosine. So what I'm going to do is I'm going to figure out the formula for tangent of alpha plus beta, but I'm going to figure it out using the formulas we already know. Tangent is sine over cosine. Sine over cosine, and just fill in your argument, whatever you're taking the sine and the cosine of. In this case, it's a sum. Okay. So let's start with the top. When we have a sine function, do we group when we use the identity, or do we mix the trig functions? Yep.
We mix the trig function.
We mix them. So it's going to be a sine and a cosine, and a cosine and a sine. Okay, by mixed, we mean that when you multiply, you have a sine next to a cosine. And what symbol goes between them? Yeah, a plus. So we're going to do a plus. And leave a little bit of space when you draw your line. You'll see why. It'll save us from having to rewrite something. So that's the top. And now let's put the bottom. Cosine of a sum. And I'll fill in all my angles in a second. What do we do with cosine? Mix or group? Yeah, group. Now we group them. So cosine, cosine. Sine, sine. And what symbol is going to go between them when we have a cosine difference? Cosine sign. Yeah, you put a minus. All right. So now we just have to fill in all our angles. Alpha, beta, everywhere. Alpha, beta, alpha, beta, alpha, beta, alpha, beta. Now that's a little bit messy because there's 8 different things written there, two factors in each term. All right, so that's our problem. But what they usually do is they simplify it a little bit so it's not as complicated looking. And what they do is get a 1 right there. Now you wouldn't know that unless I told you that. So to simplify it, I kind of have to give you that hint. I want you to get a 1 in this spot. How could you make a 1 right there? Or how can you make anything a 1? Yeah?
Oh, well, no, I mean,
Squaring something doesn't make it a 1.
how do we top and bottom things?
Yeah, divide something by itself. But if you divide this by itself, then you have to divide everything by what you divide by right here. So we're going to divide this by cosine alpha, cosine beta, and that's fine, but do it in all 3 spots. That's why I said to leave a little bit of space. So we're dividing all 4 things that we had by the same thing, which is perfectly fine to do. And the hope is we're going to get some things to cancel out and get a simpler formula than we had originally. Let's start in the upper left. Is there anything that cancels out in the upper left? Yeah?
Cosine beta.
Cosine beta. Good. We'll come back to sine over cosine right there in a minute. How about in the upper right? Yeah?
Cosine alpha.
Cosine alpha. How about in the lower left?
Everything.
Everything. Yeah, the whole thing cancels. How about in the lower right? Nothing cancels there. Okay. So let's write down what we have. What's sine alpha over cosine alpha. Yep,
Tan alpha.
tan alpha. And what's sine beta over cosine beta? Yep,
Tan beta.
tan beta. And what happens when everything cancels here? We got to put something there. Yep,
1.
put a 1. Minus. And what's going to happen with that last part? It's kind of what we just saw in the other two parts. Yep,
Tan alpha times
tan alpha, tan beta. Yep. And that's the formula for the tangent of a sum. So it's the sum of the tangents over 1 minus the product of the tangents. Now, not a big change, and we're not going to have to go through the whole thing again. What do you think the difference would be instead of doing tangent of a sum if we had tangent of a subtraction? What do you think would change in the top? Yep. Yeah, the signs would just switch. So the top would become a minus, and the bottom would become a plus. Any question? That's the tangent sum and difference identity. I guess we could do tangent 75. I think we did it in the homework. You didn't have this formula. You had to do it with sine over cosine, but let's try it. Okay. How do you break up 75? And it has to be numbers that are 30s and 45s, or multiples. Yep.
tan 45 plus 30.
Yep. Tan 45 plus 30. And now I'm going to fill everything in to this formula right here. The sum of the tangents over 1 minus the product. So that's the sum of the tangents over 1 minus the product. And you fill in your angles first, second, 45, 30. 45, 30. Okay. Let's start with tangent of 45. What's the formula for tangent on the unit circle? Once you know this coordinate right here. Yep.
Y over X.
It's y over x, and since this is a 45, 45, 90, it's isosceles. So what would happen when you divide y by x? Yeah, it would just be 1. So we get 1 in the top. Okay. Now, tangent of 30. 30's down there. What's the y value for a 30-degree angle? Yep, 1/2. And what's the x value for a 30-degree angle? Yep.
Root 2. Root 3 over 2.
Yep. No, not quite. Yep.
Root 3 over 2.
Root 3 over 2, yeah. So the 2's cancel. And when you fix that, you're left with root 3 over 3. That's the tangent of 30. Now, we've already done all the calculations that we're going to need to figure out the bottom. We did them at the top. So 1 minus tangent of 45 is just 1. Tangent of 30, root 3 over 3. Okay. Now, there's two things wrong with that. One, we don't want to leave a root in the bottom. Two, we don't want to leave a fraction within the other part of the fraction. So let's fix the fraction first. How could we fix having fractions within fractions here? Yep. Do what? Okay, we can multiply the bottom and the top by what? No, if you multiply by something with a root in it, you're going to get roots in these two spots. So we just want to make sure we don't have any fractions within fractions right now. Yep? 3. Yeah, just multiply everything by 3. Then you've got 3 plus root 3. Okay, that's better, because there's no fraction. And then 3 minus root 3. Okay, so that's a better answer. It still has a root in the bottom. We've got to multiply by something to fix that. And what could we multiply by that would cancel out the root in the bottom? We did something like this when we had complex numbers, and we had like 2 plus I in the bottom. Anybody remember what we multiplied top and bottom by here to get rid of the I? Yeah?
Would you multiply by 3 plus 3?
Yep, multiply by the conjugate. Whenever you multiply by a conjugate, it's going to cancel out what you don't want. So we're not doing I. We're going to multiply by 3 plus root 3. Okay, so let's do that out, and hopefully we get a nice answer. Okay, start in the bottom. 3 times 3 is going to give me how much? Yep, 9. What about 3 times root 3? Yep,
3 root 3.
it's 3 root 3. And what about 3 times negative root 3? Yep.
Negative 3 root 3.
And what happens when you combine a 3 root 3 with a negative 3 root 3?
They cancel.
They're gone. So we don't have to worry about the outer or the inner. What's negative root 3 times root 3? Yep. Well, it's a negative times a positive, so
Positive.
negative 3. Okay, and now in the top, we're going to do the same thing, but it's not going to cancel. So we get 3 times 3. What's 3 times root 3 plus another 3 times root 3? Yep.
6 root 3.
Yep, 6 root 3. And what's positive root 3 times positive root 3? Yep,
Positive 3.
positive 3. Okay, there's a lot of 3's here. Let's simplify all that. So we've got 9 plus 3 gives me 12. 6 root 3 over 6. So I've accomplished not having a root in the bottom. But if you look at that, what's everything in the top divisible by? The biggest thing it's divisible by. 6. So divide everything by 6. And that's your final answer. 2 plus the square root of 3. And if you check it, I'm not going to, but if you do, type in 2 plus square root of 3, type in tangent of 75, they come out exactly the same. So the trick part of this problem was done here. After we get to that step, there's no more trick. Everything else is really arithmetic, just fixing roots and fractions. Any question on the tangent of 75? All right. So now you have formulas to get rid of addition and subtraction inside of a sine, cosine, or tangent. Let's look at this. Another common thing happens is a 2 in front of the letter inside, and you don't want the 2. How could we rewrite what's inside there so there is no 2 in front of the x? Yep. You could write it as x plus x. Now that's a different problem. We've now got addition inside, which we don't want that either. But we know how to fix that. This is a sign sum identity. So let's use the sign sum identity, and that'll give you a formula for getting rid of a 2, at least with sum. When we do the sign identity, do we group or mix? Yeah, you mix it. Sine, cosine. Cosine, sine. And my symbol between the 2 parts? Yeah.
Plus.
It's going to be a plus. And what's going to be my argument for, well, every one of them? Yeah,
X.
all x's. What does sine times cosine plus cosine times sine simplify to? It's like x times y plus y times x. It's really, yeah?
2 sine x cosine x.
Yeah. There you go. So that's how you can get rid of having a 2 inside the argument. You can rewrite this as that. 2 sine cosine. That's called, it doesn't matter if you use x or you use theta, just whatever letter they use. That's called a double angle identity. So let's try when we have cosine. So we saw with sine, you can just take the 2 and put it in front and then write sine cosine. Let's see if this comes out the same. Cosine 2 theta. We want to start by writing that, hopefully with a formula we already know how to use. How can we rewrite 2 theta? Yep.
Cosine theta plus theta.
Yep. Theta plus theta. Now we've converted it from a double angle into a cosine sum identity, which we have a formula for. Can anyone tell me what cosine of theta plus theta would turn into when you start to write it all out? You don't have to give me the final answer, just the first step towards the answer. Yeah.
Cosine theta, cosine theta, minus sine theta, sine theta.
Cosine theta, cosine theta. Perfect. And what would that simplify to? Yeah.
2 cosine theta minus 2 sine theta.
What would you get if you simplified that?
2. X squared.
X squared. So you want to take a second shot at that one again?
Cosine theta squared minus sine theta squared.
Yeah. So it's going to be, I have it written right here. So we have a cosine times a cosine, which is cosine squared, minus sine times sine. That's sine squared. So no, it doesn't look the same as the one above. It looks different. But it should kind of look like something. What does this identity look like? Anything that we've done before? It's not, but it's kind of close to something. Yeah. Yeah. What Pythagorean identity does it kind of look like? Yeah, kind of looks like this one. Sine squared plus cosine squared equals 1. I'm just kind of doing this off to the side. What would you get if you solve that for cosine squared. Yeah, Malik?
1 minus sine squared.
1 minus sine squared. Take that and fill that in right there. 1 minus sine squared. I just changed that from cosine squared to that, minus sine squared. What would 1 minus sine squared be? Yep.
1 minus 2 sine squared.
Yeah, exactly. They're both right, whichever one you want to use. It just depends on what you're doing, I guess. And there's a third version. The third version you could figure out exactly the same way we just did the one above it. Except instead of getting cosine squared on by itself, get sine squared by itself. This is the only one that really has 3 different versions. And if we could do sine and cosine, what other one could we technically do automatically? Yeah?
Tan.
Yeah, we could do tan. If you ever had to do tan 2 theta, how do you change tangent into sine and cosine?
Tangent is equivalent to sine over cosine.
Yep. So if we had to, we could do sine 2 theta over cosine 2 theta, but I'm just going to give you the formula. That's what tan 2 theta comes out to. We don't do as much with tan. We do more with sine and cosine. I'm not saying it never comes up, but I don't think you're going to see this formula again in anything we do today. But the top 2, yes. We will. Okay. Does everyone have those 3? That's also the last major group of identities that I think are used a lot in calculus. Pythagorean, reciprocal, quotient, sum and difference, and double angle. Those are the 5 big categories. All right, so now let's try one. Hey, the problem says to write this using only sine and cosine. And when they say only sine and cosine, they mean no numbers next to x in the argument either. So is any part of what they gave you already okay? And we don't need to do anything to it. Yeah?
2 cosine.
Yeah, the 2 cosine x is perfect. You can have numbers outside the cosine x, just no numbers other than a 1 inside. Okay, the second part is not okay. What does the second part have that we don't want to have there?
Number in front of the x.
Yeah, we can't have a number in front of the x, so we got to get rid of that number. And we can't just take the number and move it. You got to use an identity to get rid of the number. So what do we know sine 2x turns into? Okay, and I don't mean x plus x. I want to know when we do all that out, which we've already done.
2 sine x cosine x.
Yep. Okay, and now, what could we factor out from each term? Just to make it a little simpler. Yep.
2.
Yes, you can factor out a 2. Yep.
2 cosine.
And a cosine. If you factor out a 2 cosine, what would be left inside your parentheses? Yeah. Well, we've got to have something that would be a distributive property to get back what we started with. That would give you part of it. Yep.
1 plus sine x.
1 plus sine x. Because now if you distribute it back out, you get 2 cosine x and 2 cosine sine. Right. Any question on how we factored that. So now, don't write this part, but just watch what I'm going to do. When we set it equal to 0, why would you factor an equation? What are you usually trying to find when you set it equal to 0 and then you factor it? Yeah? You're trying to find the zeros. Exactly. You're trying to find the roots. And that's the next problem. So we're going to take this, and now we're going to solve it by setting it equal to 0. But we've already done most of the work. So 2 cosine x plus sine 2x. 2x. Okay, so the directions are to solve. And they specifically say to solve between 0 and 2 pi. So they do not want all solutions. So if they don't want to know every solution, what does that mean you're not going to put on the end of your answer? Don't want this. Yeah?
Plus 2 pi.
Don't put plus 2 pi in. I know there are more answers, but they don't want to know them. Okay. All right. So the first step would be to take this and do what we did in the last problem. Get rid of the sine 2x and factor. So I'm going to copy this down. 2 cosine x, 1 plus sine x. And since you're solving for the zeros, you set it equal to 0. And the way I got from here to here, look at the last example. It's exactly what we just did. Okay. Now, when you have something times something equals 0, what do you do with each factor? It's like it was a quadratic. You take each factor and, yep, set it equal to 0. So set your first factor to 0. And set your second factor to 0. What would we do with the factor on the left to start to get x by itself? Yeah. Yeah, divide by 2. And now, normally, to get rid of cosine and get x by itself, what would you use to cancel out cosine? Yeah. Yeah, normally we'd use inverse cosine, but we don't need it because anytime you're equal to a 0, a 1, or a -1, you can just use your unit circle and it's faster. Okay. And this could be a non-calculator question anyway, on like an AP or something like that. So look at your unit circle. What angle has an x value, because that's cosine, of 0? Yeah.
90.
90. And what else? Yeah.
270.
270. There are 2 angles that have a cosine of 0. In other words, there are 2 angles that have an x value of 0. If thinking of it on the unit circle doesn't work for you, here's another way. Draw your graph of cosine and find the 2 places that it hits the x-axis. And when I say draw, I mean without a calculator, just like that. Here and here. That's the first quarter. That's the 3/4 mark. Pi over 2, 3 pi over 2, and pi is right in the middle. Okay, so that's the answer from this part. Now we have to look at the second part. Sine of x equals -1. Where would that happen on the unit circle? Remember what letter sine is, and look for where that letter equals -1. Yeah? 270, which is
Sine.
in radians.
Oh, radian. Pi.
Pi is 180.
Pi. 2 pi.
2 pi over 3 is 120. Great. 3 pi over 2. 270 is the same answer that we already got. So yes, it did give us another answer, but it's not any different than what we already had. Most of the time, this answer will not come out the same. So you don't have to write it twice. Those are all your answers. Any question on that one? Yeah.
So I get how we found the x's for cosine by looking where what x was 0,
When x was 0, yep.
and then for sine, why did we use the y? Is it because sine is y?
Sine is y on the unit circle.
Okay, so
So you have to find the coordinate that basically looks like this. You're looking for any coordinate that has a y value of -1. The only one on the unit circle, that's it. That's the only coordinate that has a y value of -1.
okay, and so for cosine, it would be the x was 0, and then we are trying to find the y.
For cosine?
Yeah.
Cosine, you're looking at x values on the unit circle coordinate. Sine, you're looking at y values. And tangent, you're looking at the fraction of the two. But there's no tangent in this problem. Yeah. So this is what 7.6 is. Okay, it's solving equations. So we'll try maybe one more of those, and that'll be it for today. So the half-angle formulas, I'm going to give them to you. Honestly, they're not formulas that I use when I'm trying to solve a problem very often. But they enable you to get rid of a 2 in the bottom of a fraction. And honestly, because I don't have these ones memorized, I could work around not knowing it. I could use other things that I know to accomplish this same result without knowing this. But I guess they are handy if you need them. And I mean, you could come up with identities for getting rid of a 3 in the bottom, a 4 in the bottom, a 5. I mean, you could do any number of identities you want. But at some point, you can't really keep memorizing every possible identity. So beyond the 5 major groups that I mentioned, usually if you need an identity other than that, you would be allowed to look the identity up and then just use it. Because in calculus, the point is not really to prove these identities, it's to figure out which one you need to use and then use it to solve a calculus problem. Okay, any question on those? And I would not focus too much on the half angle ones, at least for my class. I would worry more about like the double angle and the sum and difference. Definitely. The last thing we're going to look at is one problem in section 7.6. But section 7.6 pulls together things we've done in every section from chapter 7. So that's what sometimes makes this section a little bit harder. People don't remember like domain and range of inverse trig. That ASTC. People remember when I wrote ASTC? At least I wrote those letters on the board, even if you don't remember what they mean, but you have to kind of remember that for this. When you are solving a quadratic equation, what's one technique that you can use to solve a quadratic? Yep, factor. And we also can use that technique when we solve identities. Anyone remember the first trick that I taught you when you were doing trig identities? It was to change everything. Yeah?
I was not.
Oh, okay. Anybody remember that very first trick? Yeah, rewrite everything with one trig function. Sometimes we did it with sine, sometimes we did it with cosine, whatever. But the point is just write it with one trig function. And what's one other technique that you can use when you're solving quadratics besides factoring? Yeah.
Pythagoras theorem.
No, we can't use Pythagorean theorem to solve a quadratic equation. We can use that when we're missing a side in a triangle.
Oh.
Yeah. Yep.
Okay.
Yeah. Quadratic what?
Oh, formula.
Formula. Yep. Now, one thing that I think people don't know is they kind of understand quadratic formula in a very, very limited sense, but you can use this concept in lots of places other than something like this. Yes, that's absolutely a quadratic formula problem. I'm assuming it doesn't factor. Where a is 3, b is 8, and c is negative 17. But this problem is exactly the same as this problem. There's no major difference how you solve those two problems. 95% of the process is going to be the same. When you use quadratic formula with this problem on the left, how many answers do you get? Let's pretend like we don't have any imaginaries or anything. Yeah? Two. You're going to get a first answer, and you're going to get a second answer. And what were you solving for in this problem? Like what thing were you trying to figure out? Yeah? Well, it's a quadratic, but what are you trying to figure out? Yeah?
What x is?
Yeah, you're trying to find what x is. So when you're done using quadratic formula, your Algebra 1 or whoever teacher taught you to take each one of those answers and write that. The reason you write that is because that is what is right there. That's why you put each of the answers equal to x. Very similar idea is going to happen over here. You use quadratic formula, which I'm not going to go through and do. But you plug all those numbers into your quadratic formula. You're going to get two answers. But each answer is not equal to x. What do you think each answer would equal in this case? Yeah? So tell one more time, what would you put right here? Just one thing.
Like b to this x and sine squared.
No, it wouldn't be a sine squared.
Would be y?
Nope, it wouldn't be a y. So look at the left one. And look at where the thing was that we set each answer equal to. Now look at the right one. And find that thing in the same spot as the left one. Yes? Sine x. Always set your two answers equal to the variable or the function that's in the middle. So that would be the same right up until that step. And then how would you get rid of sine? Yep. Yep. Then you'd have to do inverse sine. Okay, but we can still use the quadratic formula. And the three things that have to happen for you to be able to use the quadratic formula: one, you have to have the same base thing here and here. And we do. Sine and sine. That's the first thing. Second thing, this exponent has to be double that exponent. Third thing, the term at the end has to be a number. Those are the three things that have to happen for you to use quadratic formula. What else? Oh yeah. We're going to need this chart. Just kind of want to review what it means real quick. What does the A stand for? Yeah? All and all what?
For sine, cosine, and tangent, in the first, what's it called? Oh,
Quadrant?
in the first quadrant, all of the answers should be positive.
Yep. In quadrant 1, all of the trig function answers come out positive. And S stands for yep, sine. And that means in quadrant 2, the sine comes out positive, the tangent and the cosine are negative. Quadrant 3, T stands for tangents are positive. And what's positive in quadrant 4? Yep. Cosine. Okay, so that tells us which trig functions come out positive and negative. And the other thing we had was 3 formulas in each quadrant. If you're dealing with an angle between 0 and 90, that is a reference angle. Does anyone remember the formula we had in quadrant 2? If you don't remember, the diagram for it would look something like this. Theta would be your reference angle, and I would want to know the arc in blue. How would you figure that out? Yep.
Pi minus theta.
Yep. So pi minus the reference angle. How about quadrant 3? If you knew that reference angle between the x-axis and hypotenuse, quadrant 3? Pi plus your reference angle. And how about quadrant 4? Yep.
Pi minus theta? 2 pi minus.
You know, yep.
Pi minus
2 pi minus what? Yeah, 2 pi minus reference angle. So when you're working with a reference angle, the ASTC tells you what quadrant you have to be in, and then the formula tells you how to find the answer in that quadrant. All right, so let's look at the last question. First thing, notice the directions before we even look at the problem. Do they want a 2 pi n on the end of my answer? No. They say to find only the solutions from 0 to 2 pi. Okay. So, does that look like a quadratic? Does it look like what I have circled right there? So remember, I mentioned 3 things that have to happen for you to be able to use quadratic formula on that. Yeah? No, it's very close, right? The last number is a constant. That's good. The first exponent is double the one in the middle. That's good. But what's wrong there that makes it not fit the pattern of a quadratic? Yeah?
You have cosine of x and sine of x.
Yeah, you can't mix sines and cosines. That's like mixing 2 different letters in a quadratic equation, like an x and an a or something. You've got to use all the same letter. So we either have to change this into sines, or we have to change that into cosines. Anyone have a guess which one we're going to try to change? And we're going to do this because we have an identity for it and we talked about this identity today.
Cosine to cosine squared.
We're going to try to change this cosine squared. What identity do we have that has a cosine squared in it? Yeah. Yeah, we have a Pythagorean identity. That will enable us to get rid of the cosine squared. We're going to have a sine squared, but that's good. We need to have all sines. What does cosine squared equal? Yeah.
1 minus sine squared.
Yep. Minus sine squared. Now fill this in right there. The 2 doesn't go anywhere. That's going to stay on the outside. So we're going to plug in 1 minus sine squared plus sine plus 1 stays the same. Okay. What do you think I would do next on the left-hand side? Yeah.
Distribute to.
Yep. Distribute the 2. So that's going to give you 2 minus 2 sine squared x. And the rest stays the same. What else do you think I would do on the left? Yeah.
My like term.
Yeah. What are my like terms?
The 2 and the 1.
Yeah. So everything you know how to do with regular algebra problems, we're just doing the same stuff. That's it. So when you combine the 2 and the 1, that's going to give you 3. Now, this is a quadratic. It is one that we can factor. But when you try to factor, there's something I don't like about this. What is it that you have right now that you don't want to have when you're trying to factor a quadratic? Yeah? Yeah? You never want a negative in front of the x squared. That's going to mess up all the rules you know about signs and factoring. I'm not saying you can't do it, but it's just not as easy. So how can I get rid of this negative in front of the sine squared? Yeah.
Multiply everything by -1.
Yeah. Multiply everything by -1. Let's read here. 2 sine squared x minus sine x minus 3 equals 0. Now, I find sometimes people look at that and they just, I don't know, they get confused because they see all the signs. Well, don't look at the signs. Pretend like all the signs are x's. All right. Yeah, so if you look at that and it seems confusing because it has sign in it, then pretend like there's no sign. Just think of it like this. 2x squared minus x minus 3. If you can solve that, you can solve the other one. It's the same thing. Let's try it without the sign so it looks less confusing. What would be your first term in each set of parentheses? Yeah.
X
And
and 2x.
2x.
Then it'd be a plus minus.
Okay, it does make a difference which one I put where. I don't know if I did it right. I'll check. And now 2 numbers that multiply to give you 3. Yep.
3 and 1.
3 and 1. And I would try them in that order. Bless you. Does that give us negative x in the middle? What does that give us in the middle? Everything else is right, but not the middle. Yeah? Gives us positive x. How do you fix it to give you negative x? Just switch the signs. Plus minus. So that's how you factor it. Now do the same thing with sine. It's 2 sine x minus 3 and sine x plus 1. We just pretended that it wasn't a sine x, we pretended it was an x. So I just changed it back. Okay. And lastly, what do we do with each of those factors?
Set them equal to 0.
Perfect, set them equal to 0. When you set the first one equal to 0, you would have to add the 3 and divide by 2. You're looking for where sine equals a positive number. Where does sine come out positive? It should be 2 places. Yep, we'd be looking for an answer here and here. How would you get rid of sine? Yep, take the inverse sine. When you do the inverse sine of 3 over 2, that's going to give you this. The other answer is pi minus the reference angle. But we don't have to worry about even doing this out. What's 3 over 2 as a decimal? Yeah, 1.5. And what's the domain of inverse sine? It doesn't go up to 1.5. What is it? It goes from, it only goes from -1 to 1. So this part, not a good example for seeing how to use the diagram in this one because you can't solve it. This has no solution. Okay, so that part, no solution. Normally you would have typed this in on the calculator right now and just written down what you get. But there's no solution. Okay, the second one, sine of x equals, bring the 1 to the other side. What angle on the unit circle has a y value of -1? There's only one angle. Yep. 3 pi over 2. There you go. And that's how you solve it. So normally we get more than one answer, but this one, the other one, was a no solution. So we'll practice more of those tomorrow. So that's the homework for tonight. That just focuses mainly on 7.5. You won't have the last problem until tomorrow night. Also on question 31, there are multiple parts, but you only have to do part A.